if you produce and you consume. Don't spend enough time just laying in meadows and watching the clouds. Got some really special clouds for today. Alrighty, let's see. So I gave you a sheet. You're probably going to want to have that sheet handy. Well, really like for the rest of the semester. And I'm actually going to add a back to it too. So I'm going to update it like for Monday when we get back. There's a couple more things to put on there. But let's talk about what we did. Just a quick review. I've got an infinite series. Don't write the indices here because in a way they don't matter. The thing to keep in mind is there's an infinity on top that's unspoken. So we're dealing with infinite series. We don't care where things start. Nothing for the rest of the semester is about where things start. It's about what happens long term. So that's why we don't need to write this. I know my index is n, n's doing something, it's increasing forever. That's okay. We just let it be, just like we practiced a minute ago. So the question here is, does this converge or does it diverge? That was the question. And the way to understand these sums was through partial sums. So here we did have our index started somewhere, doesn't matter, and went up to n. But this was just the sum of the first n terms. Whatever those are, whatever they look like, just adding up the first n things. And this is how we understand a series. We make it a sequence. So every series is just a sequence of sums getting bigger and bigger and bigger in terms of the number of things we're adding. And we're hoping that this starts to settle down. So if this settles on some value L, in other words, it converges to some value L, we say that's the value of the sum. So it's all about these partial sums. We're never actually like thinking about the whole series at once. We're thinking about just what happens in the long run. So what are the ways to determine if this happened? Well, we had this one test, and really it's a test for divergence. So the nth term test, that is an nth term test, helps us decide right off the bat, does it diverge? And in some ways, this might be one of the first things you look at, unless you know that there's other tests you're supposed to be using. But the nth term test is a divergence test. It cannot tell us about convergence. So just remember that. Can't determine convergence. Only divergence. And the nth term test said this: if the terms don't go to zero as they move out this way, then the thing diverges. That's it. So I really need the things I'm adding up, the things I'm piling up to get smaller and smaller and smaller and vaporize as we move out down the series. Some spelling errors there, but that's okay. So that was that. That's like kind of one of the primal tests. And then we had this integral test. And we used that to determine some other things. So the integral test said that if I have this series and the terms are positive, so there's no alternation, I'm not going plus, minus, plus, minus, plus, minus, then this integral from the start of the series, this starts somewhere, from the start to infinity of this function. So let me just f of x, put f of x dx there. This acts the same as the series. And what I mean by that is that this f of x is just the thing that gives the nth term. So f of n is a sub n. I'll give a quick example here in a second to make sure that this is solid. But if this converges, then so does the series. And if this diverges, so does the series. And that's all. That should all be written on that paper there. So you know you can take notes if it helps in your thinking. But this all should be on that sheet that you've got. So like for example here, if I had a series that looked like this, I got 1 over n cubed. Now we probably should be able to know that that's a p series. But if we didn't, I could use this integral here. So see how I'm replacing the n with an x and just treating it like a function? That these two act the same. So this acts like this. This converges to some finite value. I think it's like a half or something like that. And then this converges too. So you can always turn a series into an integral if you need to. I'm going to recommend not doing that. Because then I mean, we did spend most of the semester integrating and doing a lot of stuff like this, but kind of the fun of this last part of the class is not doing integration, right? Just like a whole different way of thinking about things, and that's what I'd like you to practice more than anything. So for using this, we came up with this thing about p series. And so this was part of our infrastructure, or our anchors on just understanding series in general. So if I have a series like this, 1 over n to the p, notice that the index is the thing moving, the base is fixed, the power is fixed, that this converges, and I don't know to what, it doesn't matter, because that's not our question. We don't care what they converge to in general, if p is bigger than 1. So if this exponent's bigger than 1, it converges. So I could have answered that question just with knowing about p series, right? I could just go, oh, it's a p series, p equals 1. So for example, if I had this series, 5th root of n equals 1 to infinity, what's p here? 1/5. Beautiful. That's less than 1, so the series diverges. So like that's real, that's low hanging fruit, that's wonderful. When you see a p series, yes, p series, I own this thing. And then we talked about some tests. There's a whole thing about the geometric series. We'll get into that in a little bit, but I just want to review these basic things first. We talked about the limit comparison test. So one of our first major tests for convergence was this one. We're going to do one more today. Was the LCT, limit comparison test. You could refer to it like that when you're writing stuff out, all good. I'm probably going to have a little written assignment for us so that I can see how you're writing and thinking about these things, but that probably won't come till Friday. So, test for convergence, that we compute this limit, so find, so first off, given two series, one of these I know about. So basically, when I say given, you're really only given one. And then you find one that feels like this one. And then you do this test. And so we'll practice more of that today. But I'm given this series, it feels like maybe like a p series with p equals 3 or something. And so I use that as this other series. So note, let's actually put that here. Given one, choose the other to be like the given one. That word is given there. looks like Glenn or something, the Glenn series. So we compute, and I'll give it a name here. So L equals this limit, and it's the ratio of the terms. Limit as n goes to infinity of the general term here over the general term here. And I also recommended doing this because then it makes fraction life easier. Because this thing's like going to be 1 over n to a power, and then you can just flip it, and it just becomes n to the power. So this, if L is not equal to 0, the series act the same. And what I mean by that is, I chose that one there, and if I know it converges, then when this happens, that one converges. If I chose one that diverged to compare, and this happens, then my original diverges. So that's that test. And then we got one more for today. And there's certain times you'll want to use that one, and certain times you'll want to use this one, and hopefully we'll make it really clear today what the dividing line is. So here's a new test. This is called the ratio test. This one's nice because this actually just takes the series you've got and just works with that. You don't have to choose a comparison. So this one is like self-contained. No comparator series is needed. You just do this and hopefully it works out. So given series, compute, let's call it R equals the limit as n goes to infinity of the n plus first term over the nth term. So let me write that a little differently too. That is the n plus first term. So you're going to take the general thing here, replace n with n plus 1, and then you're going to multiply by 1 over a to the n. That's probably what you're going to want to do, this form here. So you compute this, find this value. If R is between 0 and 1, the series converges. This is cool. That's really lovely and elegant. If R is bigger than or equal to 1, the series diverges. Bigger than 1, don't put equals there. Series diverges. If R equals 1, we don't have any information. We have to figure out some other thing. It could converge, it could diverge, we don't know. So put inconclusive. Deeper analysis needed. Or maybe a different test. Maybe you go to that test over there. Deeper analysis. That's it. So that's our main test for right now. So let's practice. And I think I've got like 6 series written in my notes that we're gonna play with today. So let's do these together. The first one, example, sum k over 2 to the k. Oh hell, let's just pretend it starts somewhere that we care about. What does this series look like? Can you just take a minute, write out like the first 3 terms? That I would totally recommend for every series you've got. Just like understand what is this thing. That's 2 to the k, it's not 2k. And, well, as we do these, I'll be giving you tips for what test you want to apply, and why you would do that. Just right now the first 3 terms. Yeah, nothing deep yet. Just understanding what does the sum look like. Oh, well, go a few more, right? Looks like a normal ruler, like an old English ruler with the little marks off of it. I don't know why 3/8 always makes me think of rulers, so, or wrenches or something. Does this look good? You feel good about this? Any explanation? Okay, awesome. So notice that here we have something to a power. This is almost kind of like a geometric series in some ways, except for that k on top. That's following things up. So it's not geometric because there's no common ratio, right? Because to get from here to here, I went half, but then from here to here, I went like by like 3/16 or something crazy like that. I think, is that right? Even no, 3/16 because I had to divide it, whatever. So that's not a geometric series. It's also not a p-series because p-series have a fixed base. So here we have a moving exponent, and that's the key. That's really what's going to tell me that I want to use the ratio test. So when you have a moving exponent and it's not geometric, if it's geometric, you own it. You just look at R and then you've got formulas and all that stuff. Moving exponent and not geometric means to use the ratio test. At least try that first. So let's do that then. I'm going to compute this R. Here's A sub n. So A sub n is just this thing here. What does A sub n plus 1 look like? Because we need that. Beautiful. Yeah, exactly. So A to the n plus 1. Just replace the n's with n plus 1's. Looks like that. And now you might see why I was recommending this form here, because we're going to multiply by the reciprocal of that second piece. So we're going to compute R equals lim. I'm going to write it out again. A to the n plus 1, or A sub n plus 1 times 1 over A sub n. So that's lim of that thing times the reciprocal of this one here. So that's 2 to the n goes on top now and n goes on the bottom. And that's real pretty, right? Because stuff's going to cancel. I've got one more power of 2 in the bottom than I do on top. So really, these two just turn into a half. And I'm going to pull it out in front. And then I've got n plus 1 over n. Man, that's good. Check that out and make sure that you see the moves that I made. And let me know if not, and we'll talk.
I don't know how you got the second limit.
This one here?
No, one above.
This one here?
Yeah.
Okay, so I took, you cool with these terms?
Yeah.
All right, so I took the A sub n plus 1 and just wrote that here. And then I took the reciprocal of this one, so I flipped it.
Okay.
And multiplied. That's the same thing as dividing by it.
Yeah.
Does that make sense? Yeah. Cool.
How do you get to the next one?
And then to get to the next one, so the 2 to the n over 2 to the n plus 1, that's just a half. Why?
Yeah.
Oh, okay.
Oh, okay.
Okay, because this is 2 to the n over 2 to the n times 2. 2 to the first? Yeah, add the exponents.
Oh, I see.
See?
Rules, yeah.
Cool, yeah. Yeah, exponent rules and so forth, yes. I'm glad we cleared that up, that's good. Any other questions, yeah? What's this limit? 1. It's a polynomial, right, in n. It's just, well, look, if you, all else fails, when n is like gargantuan, what's the difference between the top and the bottom? Not much. When n is a billion and 1 over a billion, 1. And it's just getting, the difference is becoming less and less. But let's talk about this if you don't see that. For this thing here, and we don't need the absolute values on there right now, they'll come in handy when we have like negatives to a power, which we will. but right now they don't really matter. So this is an infinity over infinity form, right? Do the top. Top's going to infinity, bottom's going to infinity. So by L'Hopital's rule, and I'm differentiating with respect to n, the derivative of the top is what with respect to n?
1.
Yes, and the bottom limit?
1.
Beautiful. 1. So that's nice, right? You can just crank that out like that. So this is just 1/2. And then I look at my test, or I remember that when r is between 0 and 1, I'm good to go. This is less than 1, so the series converges. Beautiful. Take a look, see how that feels. Let me know if you want to talk about any of it.
So where did you pull the 1/2 from when you actually did?
So the 1/2, when I canceled
Yeah.
that over that,
Oh,
does that make sense? So I took the 2 to the n over the 2 to the n plus 1, and that cancels to 1/2 because there's one extra 2 to the bottom. There is on top. 2 to the n is 2 to the n times 2. So the 2 to the n's cancel, and I'm just left with 1 over 2. Okay, so check this out, Olivia. If I had like 2 to the 5th over 2 to the 6th, just 1/2. And this happened no matter what n is. So this part here turned into the 1/2, and I just brought that out in front. I could have left it in here. That would have been okay too. Does that make sense?
Yeah.
Okay, awesome. Yeah, I mean, if you had that 2 in the bottom, then this L'Hopital stuff would look like this, and this would have been a 2, and this would have been 1/2. So lots of ways to get there. Good? Feel good? Okay. Here's another one. Oh yeah, there'll be some limits or something. K cubed plus 2 over k squared plus 1. So this doesn't look like a geometric series, right? Because the exponent's not moving. So let's just make some notes, like features to look for. Exponent is fixed, exponents are fixed. So it's not, I probably don't want to use the ratio test. It's not going to, that won't usually go well. Like if I use the ratio test on this, let me show you really quick. The ratio test is not helpful. So ratio test is useless. So the so a to the n plus 1 would be n plus 1 cubed plus 2 over n plus 1 squared plus 1. And then the a to the n is just n cubed plus 2 over n cubed plus 1. So when I go to do that ratio, this one right here, I take the limit as n goes to infinity. I take the n plus 1th term, times the reciprocal of this thing. And you might look at that and think, boy, I don't want to do that limit. And you might start doing something crazy, like foiling this stuff out and like turn it into something. That's just going to lead to misery, like multiplying this all out. Let's think in a deeper way, because we've been doing this. What's the highest power of n in this expression? 3, right? So this is like n cubed. What about this one? N squared. And there's literally going to be a 1 as the leading coefficient. So what is the net effect? What is the highest coefficient in the top? We have n to the what? That times that? What's that? N to the 6th. So this is like n to the 6th over what? Oh wait, n to the, hold on, I didn't copy something right. What did I fuck up here? That should be a 2. There we go, sorry. So that's a 2, there we go, okay.
Then end of the fifth.
End of the 5th over end of the 5th, yeah? And that would be what in
One.
limit? 1. You're getting like serious like finger exercises today. So this would go to 1. This limit would equal 1. What does the ratio test say when r equals 1? Inconclusive. No, yep. No info. So this is inconclusive. And that'll always, almost always happen in a situation where you don't have a moving exponent somewhere in the problem. So this doesn't help. So it's okay if you went that route first, but you just spend a lot of time not really learning anything. Shit. I thought I said that, okay, so this is, we have this test, and then we have the limit comparison test. What is this fraction in here like? When k is big, does the +2 and +1 matter?
No.
No. So this is kind of like k cubed over k squared. What's happening to that as k gets bigger?
Blown up.
It's blowing up, right? When k is 1,000, this is a billion, over a million. When k is, I don't want to keep doing that shit. But this thing's gonna be a lot bigger than the bottom. So what is the limit? It's infinity. So let's check this out. Look at how the top is bigger. Just notice that right off the top, that this thing doesn't go to 0. Like when k is big, you're adding big ass number over big ass plus big ass number, and they're getting bigger and bigger ass all the time. That ain't gonna converge. So what test do you think I wanna at least quote here or mention? Nth term test, exactly. So let's just write this all out though. So since k cubed plus 2 over k squared plus 1 is going to infinity as k goes to infinity. It doesn't matter if you use n's or k's, it's all good. You can use whatever letter you want there. By the nth term test, this series diverges. So things to look out for. Like, that's what I was saying, like, before you even start to test things, look at what you've got. Just really look at the series you've got in front of you and see if you can do like kind of a meta-analysis just right up front. A little bit of triage. What do I have? What am I going to try? Do I even, does this thing even have a hope of converging? Does that make, are we all good here? Yeah? Yes?
Is the nth test the same as the p test?
No. The nth term test is looking to see if the terms die out. In a
Okay.
p-series, I like that question, because in a p-series, here's your general term,
Oh, because
and they always die out,
okay.
but they may not converge. They have to go to 0 fast.
So it's only on the bottom, but this has like 2 polynomials, so it's supposed
Yeah.
to be 1.
Yes,
Okay.
yes. So this could have, like, if these had been reversed, I would have gone to the comparison test. If it had been this, what is that effectively like?
1 over k.
Yeah, 1 over k. Do you see that? That this is like k squared over k cubed. It's like 1 over k, and that is a p-series. So if I had had this, I couldn't have employed this test because the terms go to 0. They just don't go to 0 fast enough to actually get a finite sum. All right, let's do another one. Your turn. Here's a tip. When you see a factorial, what you're going to see right now, use the ratio test. So factorials and powers, moving powers and moving factorials are a ratio test ready-made. remember the restroom. I'll be right back. Sweaty, and I'm getting cold from that. Jesus. You don't need to go. Thumbs up or thumbs down on convergence? So, that was a very hesitant unit. Thumb wasn't popping up much. You might want to take, when you know you're using the ratio test, you might want to just like write those things out to the side, what AN is, what a n plus 1 is. There's a little bit of trickiness here with these factorials. Does that look like what you're all trying? Is everybody trying this? Good, good. Cool. So let's talk about those factorials, because this is gonna happen a lot. When you have a ratio of factorials, probably best to just do a little thinking until you get savvy about this. But that's n times n minus 1 times blah, blah, blah. Eventually, you'll end up at 3 times 2 times 1. Eventually. As long as n's bigger than 3, you'll get there. So, and n will be bigger than 3 because we're letting n be insanely large. And then down here, this is n plus 1 times n minus 1 times blah, blah, blah. way down to 3, 2, 1, and then you see that this stuff cancels, right? So everything cancels from the top factorial, and you're just left with 1 over n plus 1. So that's like essential. If that didn't happen, or maybe you did it, so you could have possibly concluded this some weird way or something. The one thing I don't ever want you to do is think some garbage like this. I mean, don't ever do that. That's bad. That's bad. There's very few things in math that do that through parentheses. So we can simplify here, and I shouldn't put that back in my bag because I keep making the same mistake. Oh, God, that's satisfying. Wait, did I fuck this up?
No.
No, I didn't.
I don't think so.
I don't think so. Oh God, okay, yeah, okay, it's okay. I was like getting really scared. I was thinking I was gonna conclude that it diverged. Because I got scared because there was a 10 left on top. Silly boy. Does this look good? Yeah, and now that's lovely, right? That just goes to 0. And since r is less than 1, and that's really all we care about, the series converges. It hella converges. That's a special type of convergence. Sound good? We feeling good about this stuff? Yes, any questions? Anything you want to talk about? Any uncertainties, clarifications? Happy to talk.
Can you talk about that factorial thing again?
Yes, we could, absolutely. Get some space over here. So let's do a little practice with that stuff. So let's say I had something like this. If we can do this, we can do lots of things. So the top would be n plus 3 would be the largest thing, and then I would be subtracting 1 and working my way down, and then blah, blah, blah. And I'm going to stop there, and I probably will see why. You either see why now or you will see why in a second. And then the bottom, Josh, I'm going to write that one out. Is that making sense? Yeah. So notice here that this larger factorial contains the lower one. I just have to figure out how much. And I'm going to cancel. So I got n minus 1, n minus 2, n minus 3 would cancel. And then all this stuff would cancel. Because all this stuff here is the same as this stuff. All this stuff here is the same as I have below. So that was what I was doing over there when I had the n plus 1 factorial in the bottom. Does that make sense now?
Gotcha, okay.
Cool. So this would end up just being this expression. If you had been in my discrete math class before, you would have heard someone wailing that they had to write out multiple terms like this. We're just tougher than that. All right, let's do a couple more. So I'm kind of thinking Friday would be a really good day for us to work on this web work together. I don't know if I'll say much new stuff. I might say a little bit, but let's plan on definitely working together on this stuff, because I'm going to be taking a lot more time than I thought I would. So, ooh, boy, oh, this one's exciting. What the fuck? Lots of things happening. Looks like a P-series, looks like a geometric series, but we know that once there's a geometric series involved, what test?
Ratio.
Ratio. Yeah. Let's start talking like Scooby-Doo there. If you can do this one, you're in really good shape. I had another one here that would be fun to do. What you thinking? So how did so you did some this canceling is a lie. Yeah, it can't cancel. Yeah, even if you factored it out. Oh, I don't think that factors like that, because this would be k squared plus, see, your last term here would be 1, and the last term here would be 3, right? So k squared, I agree with this part, is k squared plus 2k plus 3, but that doesn't factor into that. And I don't think this actually does factor, because you the last, you would have to have a 2 and a 3 and a 1 as your last, your L would be a 3 and a 1. Yeah. Oh, I see. Oh, I'm seeing. I'm sorry. You were okay. This wasn't your final factorization. Gotcha. Oh, okay. Oh, okay. Cool. So let's really quick. Is it okay if I write it here? So you've got k squared plus 2 over k squared plus 2k plus 3. So none of this actually cancels because these are sums. So, but you could do the limit from here. So what's that limit going to be as k gets bigger? So we got a polynomial over polynomial. So So when k is really big, what is the top like? Does the plus 2 matter is what I'm asking? Not really, right? And then when k is really big, the 3 certainly doesn't matter, and this doesn't matter as much either. So it's kind of like k squared over k squared. What is that? It's k squared over k squared. Yeah. So this piece goes to 1. And then you have that 2 on top. Does that make sense? So the 2 is perfect. Like, that's perfect. It was just your canceling here that's not true stuff. So I would just pull that 2 out front. I would have this inside. This is the limit part, and then the 2 would be 2 times the limit of this thing. Does that make sense? Yeah. That's okay. All right. Maybe we should talk about this. Do we feel okay up to here?
Yep.
Yep. Yeah. Okay. So what is this and this cancel to? 2. Yeah, beautiful. Just bring that out in front. Kitcher, are you cool with that? All right. Man, what happened here? I walked around without a lid on. That's the problem. Whew, that is messy. Good Lord, it's getting worse all the time. So the 2, I'm bringing the 2 out front. So then I'm left with this. Oh, that's so beautiful. Like that. Yeah. So if you were to multiply out this bottom, it would be n squared plus 2n plus 3. Let's just go ahead and do that, and then I'll argue it a different way. None of that stuff cancels because those are sums. Can't cancel a fraction, a sum in a fraction. You can only cancel products in a fraction. So none of this stuff matters. What is this limit going to here?
1.
It's going to 1. Is that the part that's not making sense? Should I explain that? I can explain that like 500 different ways. Should I explain it some more ways? Okay. So let's talk about that limit without L'Hopital's rule. So this is 2. L'Hopital's rule will get you to 1 after 2 applications. That's infinity over infinity. First time you get like 2n over 2n plus 2. Second time you just get 2 over 2. So you could get L'Hopital's rule to take you to this 1. Or you could do this. You could argue it like this. And I'm going to show you one other thing too. Divide the top and bottom by n squared. So I'm multiplying the top by 1 over n squared. And I'm going to multiply the bottom by 1 over n squared. And I did the same thing to the top and the bottom, so I didn't do anything to change the actual value. So see what I did? Divided the bottom by n squared, divided the top by n squared, and I got this. What happens to a fixed thing over a thing that's blowing up? 0. So these all go to 0. So now I can get 1 that way. So I can get 1 that way. Here's a good rule of thumb. And let's write it in terms of n. N. So if you have the limit as n goes to infinity of a polynomial over another polynomial. We've got options here. So if the degree of the top, and what I mean is the highest power, is bigger than the degree of the bottom. It's like this is third, this is squared. Then this goes to plus minus infinity. Then the limit. It's not both, but it depends on if they're opposite signs for your leading coefficients. It doesn't matter. That would be divergence. That would be bad. If they have the same degree, let's do the other one. So if the degree of the top is less, strictly less than the degree of the bottom, where does that go?
0.
0, yep. Squared over cubed shrinks to 0. So then the limit equals 0. If they have the same degree, then the limit is the ratio of the leading coefficients. Limit equals ratio of leading coefficients. And leading coefficients are the coefficients on the highest power of n. So we can come to this one and see same degree, so 1 over 1. And just get that limit out. That's a nice thing to have just ready. And then look, there's always L'Hopital's rule too, right? So there's 3 different ways to see that that goes to 1. That's not like a way to see it, that's just like something I told you. These are like ways to do it, but you can use these ways to get that result over there. We good? Yeah, all right. I'm done. I'm totally spent. I'm totally spent. Do you want to call it a day? Let's call it a day. Let's work on Friday. On Friday, come on in. I mean, please spend some time on this before Friday.
I don't think it's up.
It's not open yet.
It's not like showing up on.
I was probably really crafty and made it open right after class.
It usually shows up on web work, but it wasn't showing up after
Wasn't
class
even like an
or during
option.
class.
Maybe I did something weird.
Yeah, 'cause it will usually show up and be like won't open until.
Okay.
Yeah.
Could someone please send me an email, just title web work? It doesn't have to have any formality or niceties to it.
I got them.
Thank you. You got it?
Yeah.
Thanks, Lou. I'll check it out as soon as I get home, which will be as soon as possible.